There is one crop that almost nobody grows for machines, or for fuel, or for animals. 95% of it goes straight into human mouths. About half the people alive depend on it to survive, and growing it means deliberately drowning a field. Start with the raw numbers, because they are hard to hold in your head. Every year the world harvests over 700 million tons of rice, grown across roughly 170 million hectares of land. That is an area larger than most countries on Earth, planted with a single grass. Once it is milled down to the white grains you actually cook, that is still around 480 million tons of food. And unlike almost every other major crop, this is not an industrial input. It is dinner. For roughly half of humanity, including very nearly everyone across East and Southeast Asia, rice is not a side dish or an occasional choice. It is the foundation of eating itself, the thing that stands between a family and hunger. To see why rice is different, compare it to corn. Corn is the biggest grain on the planet by tonnage, but most of it never touches a human plate. It becomes cattle feed, ethanol for fuel tanks, sweeteners, and industrial starch. Rice is the opposite. About 95% of the world's rice crop is eaten directly by people. There is no vast ethanol industry burning it, no enormous feedlots swallowing it. When a rice harvest fails, the effect is not a slightly pricier steak months later. It is immediate, and it is measured in hunger. Rice provides more than 20% of all the calories consumed by the human species, and in parts of Southeast Asia, that figure climbs as high as 76%. 3/4 of everything a person eats traced back to one plant. Now to the strangest part of growing it, the water. Those mirror-flat, shining paddies are not flooded because rice needs to live underwater. Rice will grow perfectly well in a normal damp field. The water is there as a weapon. Rice happens to tolerate standing water far better than almost every weed that would otherwise compete with it. Flood the field and you drown the competition while the rice carries on, breathing through special air channels that run down its stems into the roots. It is chemical-free weed control, invented thousands of years before herbicides existed. The water does other work too. It buffers the crop against temperature swings, holds warmth through cool nights, and releases nutrients from the soil. One simple idea, standing water, solves several problems at once. But making a field hold water is genuinely difficult engineering. A paddy needs to be almost perfectly level, because if one end sits even slightly lower, the water pools there and leaves the high ground dry. Farmers have spent generations leveling these fields by hand and by buffalo, and today by laser-guided blades. Underneath, the ideal paddy has a hard pan, a compacted layer of soil that stops the water simply draining away into the earth. Around the edges sit low earthen walls called bunds, holding everything in. And the whole system needs a reliable supply of water that can be let in and drained out on command at the right moments in the season. A rice paddy is not a field that happens to be wet. It is a shallow, carefully built reservoir that grows food. Now imagine trying to build that on the side of a mountain. That is exactly what generations of farmers across Asia did, and the results are some of the most breathtaking landscapes on the planet. Rice terraces step down steep hillsides in enormous green staircases, each level a small flat paddy held by a wall of stone or packed earth. Water is released at the very top and allowed to trickle down from terrace to terrace, using nothing but gravity, feeding each level in turn. Some of these systems are well over 1,000 years old and are still farmed today by the descendants of the people who cut them. They were built without engines, without concrete, without surveying instruments. It is one of the great feats of engineering in human history, and it exists purely so that steep, useless ground could grow rice. Rice is also traditionally one of the most labor-hungry crops there is. In much of the world, it is still not simply sown into the ground. Instead, seeds are germinated densely in a nursery bed. Then each young seedling is pulled up and pushed back into the mud of the paddy by hand, one at a time in neat rows, by people bent double in ankle-deep water for hours. Transplanting like this gives the rice a head start on weeds and produces a more even crop, but the labor cost is enormous. Where land is fragmented into small plots or terraced onto slopes, big machinery simply cannot get in. That is why rice farming can look almost unchanged from 1,000 years ago in one valley, and be fully mechanized with transplanting machines and combined harvesters in the next. It is worth pausing on how unusual rice actually is as a plant, because most crops would simply die in these conditions. Drown a wheat field or a corn field for weeks and the roots suffocate and rot. Rice does not, because it carries a piece of specialized plumbing that most grasses lack. Running down through its stems and into its roots is a network of air channels, essentially internal snorkels, that carry oxygen from the leaves above the waterline down into the submerged roots below. That single adaptation is the entire reason paddy farming is possible. It lets rice sit calmly in standing water that would kill its competition, turning a flooded field from a disaster into a private, protected growing space. Almost every strange thing about how rice is farmed traces back to this one biological trick. Because water has to be captured, leveled, shared, and released on a schedule, rice does something unusual. It forces people to cooperate. A single farmer cannot really build a paddy system alone. Terraces, channels, and bunds have to be planned and maintained across whole hillsides, and the water has to be allocated fairly between families upstream and downstream, season after season. Historians have long argued that this shaped how rice-growing societies organized themselves, pushing them toward dense villages, shared irrigation duties, and tightly coordinated labor at planting and harvest. Compare that with a wheat farmer on a dry plain, who can largely plow, sow, and reap on their own schedule. The crop in the ground quietly influenced how communities were built around it. For most of history, all this effort still produced fairly modest yields, and Asia lived under a constant threat of famine. Then, in the 1960s, that changed. Researchers at a rice institute in the Philippines crossed varieties to create a new semi-dwarf plant. Older rice grew tall, and when it was heavily fertilized, it would grow taller still, become top-heavy, and fall flat in the field, ruining the crop. The new short, stiff-strawed rice could carry a much heavier head of grain without collapsing, so it responded to fertilizer by producing more food instead of more stem. Yields roughly doubled. Combined with irrigation and fertilizer, it was the heart of the Green Revolution in Asia, and it is credited with feeding hundreds of millions of people who might otherwise have starved. One plant breeding decision quietly rewrote the demographic future of a continent. All of this comes with a bill, and the largest line on it is water. Of every crop humanity grows, irrigated rice consumes the greatest volume of water. Keeping a field deliberately flooded for much of a season means enormous quantities are lost to evaporation and seepage, quite apart from what the plant actually drinks. In regions where rivers are shrinking and groundwater is being pumped faster than it refills, that is an increasingly uncomfortable position for the world's most important food crop to be in. It also ties rice tightly to the monsoon. A late or weak rainy season does not gently reduce the harvest. It can decide whether tens of millions of people can afford to eat that year. There is a second cost, and it is invisible. When soil sits underwater, oxygen cannot reach it. In those airless conditions, particular microbes thrive, and as they break down organic matter, they release methane, a greenhouse gas far more potent than carbon dioxide over the short term. Multiply that across 170 million hectares of flooded fields, and rice paddies become one of the significant human sources of methane on the planet. This puts the crop in a genuinely difficult position. The flooding that suppresses weeds, buffers temperature, and secures the harvest is the very same flooding that drives the emissions. You cannot simply switch it off without consequences for the food supply of billions. Here is something that surprises people. Despite being the staple food of half the world, rice is barely traded internationally compared to other grains. The overwhelming majority is eaten in the country, often in the very region where it was grown. Only a thin slice ever crosses a border. That sounds harmless, but it makes the global rice market dangerously fragile. Because the traded volume is so small relative to production, a modest disruption anywhere sends violent shocks through it. When a few large exporters restricted sales during the crisis of 2008, world rice prices spiked to extraordinary levels within months, triggering panic buying and unrest in importing countries. A crop that half the planet depends on turns out to sit on one of the thinnest, most easily panicked markets in global agriculture. Production is also strikingly concentrated. China and India together account for roughly half of all the rice grown and eaten on Earth. Add Indonesia, Bangladesh, Vietnam, and Thailand, and you have captured the overwhelming majority of global supply. This means the world's most important food crop depends heavily on the weather, the policies and the politics of a small handful of countries, most of them clustered in the same broad climatic region. A monsoon that misbehaves across South and Southeast Asia does not cause a local problem. It moves the price of survival for people thousands of miles away who have never planted a seed in their lives. So researchers and farmers are now trying to rewrite parts of a system that has worked for millennia. One approach, called alternate wetting and drying, lets the paddy dry out periodically instead of holding water constantly. Done carefully, it can cut water use substantially and reduce methane emissions without meaningfully hurting yields. Another approach skips transplanting altogether and sows seed directly into the field, saving enormous amounts of labor, though it demands better weed control precisely because the water is no longer doing that job. Breeders are also developing varieties that survive being completely submerged by floods for weeks, and others that tolerate drought or salty soil as seas creep into low-lying deltas. Every one of these is an attempt to keep rice feeding the same number of people using less water and doing less damage. There is one more stage most people never think about, and it happens after the harvest. What comes off the field is not the white rice in your cupboard. It is paddy rice, each grain still sealed inside a tough, inedible husk. Milling strips that husk away to reveal brown rice, the whole grain with its bran layer still attached. Polish that bran off and you finally get familiar white rice. Every step trades nutrition for shelf life and cooking convenience. The bran holds much of the vitamins, minerals, and oil, and it is exactly that oil which makes brown rice go rancid far faster. Communities that historically shifted hard toward polished white rice sometimes paid for it with deficiency diseases, which is why some countries now fortify rice or promote parboiling, a process that drives nutrients from the bran into the grain before milling. What makes rice remarkable in the end is how little attention it gets for how much it does. It has no ethanol lobby and no vast industrial supply chain turning it into 1,000 unrecognizable ingredients. It is not hidden inside your food under another name. It is simply cooked and eaten in enormous quantities by more people than any other single crop feeds. It shaped where civilizations could form, how societies organized labor and water, and what the terraced landscapes of half a continent look like. And it still does the same job every day in hundreds of millions of small fields, largely out of sight of the parts of the world that talk most about food. So the next time you see a paddy shining like a mirror, remember what you are looking at. A built reservoir, 1,000 years of engineering, and the single most direct link between a field and a human meal on this planet. Follow along for more of the hidden systems behind the food we eat.